that's not the case. But nothing would surprise me. I do see sort of internet chatter about summer school and how they're going to probably have to do summer school in a virtual way like this. So we'll have to see how that plays out. Anyway, thank you so much for being in class. I really appreciate it. This, in my opinion, is lecture number 6 or class meeting number 6 in the post-COVID-19 world. And of course, we do live in strange times, no doubt about it. I'm really happy, as I said, that people are here regardless. I mean, 20 people, 20 students is a great number to have. There are some people that have just plain disappeared. And I can't name names, but there are people who have just plain disappeared. Despite my efforts to get a hold of them, they just seem to be gone. And I'm not really sure what that means. I mean, it could mean that somebody doesn't have a computer at home, or they don't have internet access. I mean, it's not like you can go to the library to get internet access now. Maybe you read by email that out at downtown campus and at Pima West, they have Wi-Fi parking lots now, where you can drive your car, connect to the Pima College Wi-Fi, and do online work under those circumstances. I'm not sure what that would be like. You're not allowed to have more than one person per car. You're given a limited amount of time. I mean, you can't sit there for 3 hours unless no one's there. I have a feeling if there's a waiting list to get into the Wi-Fi parking lot, that they only are going to let you have a half hour in the Wi-Fi parking lot. So it's just hard to know why some people have kind of disappeared off the face of the earth when it came to this, except you think, wow, it's a big electronic thing. There are people who don't have computers. They don't have a cell phone. I know there's people who work on a cell phone, do this sort of stuff on their cell phone. In fact, I got to tell you a funny story, because earlier today on my other class, someone left the microphone open while they took a restroom break. And it was everybody in class could hear them in the restroom and flushing the toilet and all this kind of stuff. Because I'm guessing
Were they go number 1 or 2?
What'd you say?
Did they go number 1 or 2?
It sounded like they were peeing.
Oh, that's good. At least it's not weird.
Yeah, that's just like water dribbling. But then you could hear the toilet flushing was very loud. I'm just saying, you might want to be aware that you could have a microphone on that would allow us to hear anything that you're saying. I'm going to just look at the chat list real quick while we're here. And it's basically just people saying hi. And that's true. Somebody, I did say the good old days, back in the days when we actually had a classroom. And I remember it so well. I would meet you at the class and go, good morning, class, even though it was 5:45 at night. And then we could go out in the desert and we do all kinds of, stuff like that. Well, anyway, this is our new reality. And so we just got to cope with it. Nothing we can do except cope with it, because believe me, the ultimate goal here is that everybody who's participating and working is going to get through this class and get a good grade in the class. That's the ultimate goal. So if you keep coming to class and you do your best job to submit the things I've asked you, and you sort of stay on top of the material, then you're going to get a good grade in this class, and you're not going to have to repeat this class, and we will have successfully completed the semester. I assure you. Okay. I can't actually make that promise in some of my other classes, because those classes are, they're not, kind of gen ed, non-majors kind of classes. And those classes, I actually have no choice but to flunk people, and because I can't let them go into the next class if they're not prepared for it. But in this class, no, hang in there. Do your best to do the best work that you can. Turn things in, stay on top of it, and we are, and we will end the semester successfully on time, etc. I do not know what they're going to do with summer school. I was planning to, or hoping to teach summer school, but I don't know exactly what the format of summer school is going to be right now. And again, they're hoping, I know they're hoping that by the fall, everybody will be back in regular classes. I don't know if these have to be social distancing classes or whatever. But anyway, speaking about social distancing, I noticed that when I travel around the town, I see people doing social distancing. I noticed there's, pieces of tape on the floor in the Circle K, and there's, everywhere you go, there's like sneeze screens in front of the cashiers. Many people are wearing gloves. Many people are wearing, face covering masks of one kind or another. I've seen some really creative ones, including ones that, have like animal faces on them and that kind of stuff. I mean, people are doing their best to, to survive the COVID-19 plague as it exists. I'm still eternally optimistic that, yeah, Lisa, me too. It makes me very nervous when I'm in the store. So I'm still eternally optimistic that we learned some lessons by observing the people back east when they went into full scale, infection rates, like in New York City. And we've learned some lessons, so people are social distancing out here now. And honestly, I think that means that we've flattened the curve, I hope. Last time I checked, I saw there was something like 28 cases in my zip code. And so, there's certainly people, whatever. Yeah, you're right. There's people who have not gotten the memo and they're out there just cruising around as if everything was, normal. But I don't really think things are normal now. And I personally hope that the future of Pima College is not that we do everything online. I really hope that that's not true. I hope that we're going to figure out how to do it. Of course, once there's a vaccine, people can get vaccinated, and so everybody will be pretty much immune, we hope, then things will go back more to normal. But anyway, so again, thanks for being here. I appreciate your patience with me, and there's lots of reasons to be happy that you have to be patient with me. I've been asking you to do things and turn them in, and I've been very slow at grading them. And again, I'm not trying to make an excuse, except that it does take me a lot longer to process things now than it ever took me before. So I'm doing my best, and I promise that by the time we meet again on Monday, I will have D2L updated with many grades in it. I'm going to spend a lot of my time this weekend working on that. Okay. Since I'm stuck in my house most of the time, you think I would get more done. So far, just getting organized and trying to keep on top of everything. Now, what I have been doing, of course, is I've been trying hard to convert things to YouTube and post things on YouTube. That's challenging, but it's not hard to do it from YouTube. It's just that I think maybe because of my internet service, things download slowly and they upload slowly, but I will keep you appraised and let you know about what things are available on YouTube, because I know you just want to spend all day watching me on YouTube. And the only people who can get to those YouTubes are the people I give the links to, so I'm not getting famous or infamous as a biology teacher. Okay, so I'm glad I thought a little bit about my internet service. I've had no problems the last day, or I didn't have any problems today. Last time in the afternoon, I was having all kinds of problems, but they did something. They, boosted my internet service or something like that. So it seems to be working better now. But I want to say the same thing I said the other night. If we are not pretty darn close to the end of class and the internet crashes, then I am going to immediately send out a new link so we can come back together. Okay. If it's the last 15 minutes of class, then probably I won't. We'll just meet again on Monday. But the bottom line is that if it happens a third of the way, a half of the way, even 3/4 of the way through class. And there's still a significant amount of time and I haven't really had good closure, then I am going to send you a new link so that we can get back together again. So I don't know, I guess the best news that I've had in the last day or so was that I got that money from the government. I couldn't believe it. I mean, I know they were talking about this relief package and everything else. I thought, you know what? If I ever get any money from the government, it'll probably be 6 months. I'll get a check in my mail or whatever. But no, last night at midnight, bang, they deposited money in my account, and I can't remember the last time the government gave me any money like that, except money I've earned by working for Pima County. But anyway, it seems as if people I've checked with are mostly getting that money, and it seems like it's mostly about $1,200 per person, plus an additional $500 or $600 if you've got kids. I mean, they're giving you, I think, $500 or $600 per kid. So anyway, I don't know. I know that I know that a number of people have gotten the money, and it's just a matter of time. I think I thought maybe they were starting with the M's. Seems crazy, but I mean, I got it. My daughter got it. Some of the other people I know who are right, who probably should have, I think, would get it. Some of those people have not got it yet. I'm looking at my screen. It looks like my screen is just plain frozen. I'm not sure why. All right, I saw a tiny bit of movement, but my screen is frozen now. I'm not sure what that means. Can anybody hear me talking?
Yes.
Okay, good. But basically, here we go. We're back. Thank you. So anyway, I guess that's about the best news that I got in the last 24 hours. Of course, I had to pretty much pay all the money to places where I sort of used up money trying to survive in these days. Anyway, bottom line is that we've got a good class tonight, and I've got stuff that I'd like to cover. But let me again say it: if I crash or we somehow the class comes to a close before normal class time, unless it's in the last 15 minutes of class, then unless it's in the last 15 minutes of class, I'm going to restart the class so we have closure at the end. Okay? So thanks everybody for telling me that you can see me. I'm sorry that you can see me, really, because I feel like I am. I see myself too, and I kind of think, whoa, kind of wish I didn't see myself because the way the cameras are, I think it's certainly not very flattering. All right, let's talk about some classroom details. One is that I am working on continuing to download, and I will be uploading, and I will let you know about files that you can go back and look at so that you could take a look at recent lectures. Now, I just got it today. All right, so I'm going to go over here real quickly and take a look at here. So don't anybody look in my email, please. But where am I? I sent myself. I thought I had sent myself. Where is it? 1:48 p.m. Benefits questions. Where is it? Oh, there it is. So here's the YouTube video for the last lecture that I gave. So because I'm kind of, lazy, maybe I'll just run this last lecture. I'm only kidding. But here's the video for the last lecture. Let me post this in the PowerPoint. Right, I don't need to look at this anymore. But I'm going to copy down this link. Copy down this link. Come on. Okay, try this again. No. Why is it being such a pain? All right. I'm going to go back to our meeting. I am going to, it's probably not going to let me do this, but let's see if I can do it. Here's where we were last time. And so let's try and stick this in here somewhere. Well, yeah. I want to see if I can post this here, but I guess it's probably not going to let me post it anyway. All right, sorry. I apologize. But again, we've got, I do want you to be aware that I am, did not want to click on that. I wanted to, I'm going to put that, yes, I know I'm presenting. Oh, this, I'll enlarge this in case anybody wants to write it down. That's Bio 105, Lecture 5. That's my last lecture. And I'm going to put this up big in case anybody wants to, if anybody wants to copy down this link. Here is, can everybody see this?
No, I can't see you.
Okay, well, let's double check and see what's going on here. You can't see me or you can't see this document?
I can't see you. I can't see anything. I just have blank screen.
Really? Okay.
Yeah.
As I'm presenting.
I can.
Right, so here yeah, I'm pretty sure other people can see me, Carol. I don't know what's going on with your computer. But where was I a minute ago? I'm going to pull this document back up. Was this it here? Don't need this egg data. This is what I was trying to pull up. And I just wanted to show you, if you were interested, that, sorry, new people logging in. If you were interested in this link, I will post this link in a PowerPoint, but take a look. Here's the newest YouTube link. This is Bio 105 Lecture 5. So that's the lecture from Monday. So there it is, Bio 105 Lecture 5, https:// youtube.be/capital N lowercase u capital X, capital N lowercase u lowercase x 83 lowercase q lowercase f 24. Wow, I don't know if that's a 0 or this is a 0 or an O. I don't know, but that looks like a capital I to me. So anyway, I am working on this. It takes forever to upload. It takes forever to download the document first and then upload it onto YouTube. But once it's on YouTube, you should be able to see it if you have the link. If you don't have the link, you won't be able to access it. You can't, I don't think you can search it or something like that. I don't think you can, but you know what? I don't feel like I don't know that much about it. So if anybody wants this, oh, I know what I'll do, or at least for now. I'll copy this and I'll paste it in the chat. All right, so there it is. That's the easiest way to deal with it for sure. Oh, so we're back. So I wanted to mention that. Come on, close down document. There we go. I wanted to mention that. And I wanted to mention that I have posted some things. Hi, Misha. I wanted to mention I posted some things. So first, I want to make sure that you know that quiz number 13, that's the quiz that deals with population interactions, which I will review briefly today. Population interactions is posted as, believe it or not, document 0010. And you know, that puts it right at the top. Okay. And then what was due today was quiz number 12. Thank you, Jessica, for pointing that out. Quiz number 12 was due before class today. That was the quiz that dealt with biogeochemical cycles, which is the way we refer to matter recycling in ecosystems. So quiz number 12 is due. Quiz 13 is posted as, again, document number 0010. And I know that's weird, but I mean, I'm trying to put this stuff up front. I thought if I put 0010, it'd put it right after 009, but instead it put it at the top of the list. So it's right in the very top of the list. And then I also posted, a new document today, which was, you know what, I need to double check this, but I posted document 0011, and actually, I thought it was population ecology. But you know what? I'm going to go and I'm going to look at it. Okay. I apologize. I think I can go and I can look at it and double check to see if that's correct. I don't want to give you bad information. So just give me a second. I mean, I'm assuming people can see what's going on here on my desktop. I'm just going to go right into our Drive folder. And, you know, by the way, just as a note, people have been telling me, why are you emailing me in the middle of the night with a Google Meet? And I kind of want to go, well, why are you opening your computer in the middle of the night? But I've noticed that when I send an email out, it ricochets back to me again and again and again sometimes. So believe me, just for the record, I am not going to open a Google meeting at 11 o'clock at night. I am absolutely not. If somehow you get an email from me, that's an email echo. It's not what you would think it was. Okay. All right. So I was wrong. What I posted as document number 0011 is actually the new PowerPoint that we may start looking at tonight, or if not, it's going to be the focus of our class on Monday, and it's on population ecology. And that's why it's called, remember, we've got here 0010, quiz 13 on population interactions. That's the one that's due on Monday. And then the brand new PowerPoint, and Sydney or Sarah, if you would remind me, I will send that PowerPoint to you. Just please send me an email, okay? Because I want to send it to you.
Thank you. I will.
I'm a little bit overwhelmed with all the complexities of stuff right now. I mean, I have to admit it. I am, you know, doing the regular class, trying to do that as best as possible, trying to grade things on the internet, and then trying to download and upload lectures and trying to keep all that stuff straight. I am sorry. It's stressing me out a little bit. If it wasn't for my Polar Pop, I don't know how I'd survive. And so anyway, bottom line is that those things are posted and ready for you to look at. So you could take a look at the new PowerPoint if you would like to. Okay, so are there any questions about anything that we've covered so far or whatever? Let me, if anybody has questions, of course, remember, that what you absolutely need to do is jump in. Just don't worry about disturbing me. It's not going to disturb me by any means. I'm used to being in front of a class and answering questions all the time. I think everybody knows I'm relatively patient about that kind of stuff. I should take the government money that was sent to me and hire an assistant. That's what I should do. I need a personal assistant. But anyway, just jump on in. Can't raise our hands, and so just have to open your microphone and jump on in. Was that a question?
Oh no, I just said I got you. I'll be your personal assistant.
Oh, I should
I'm
be.
not-
I mean, that's what I should do, but and I probably, I mean, it would be nice just to help me keep track of stuff. I could get somebody to just upload and download and then tell me what's been uploaded and downloaded, and that would be great. But all right. So anyway, here we are. We got, I guess, about 23-ish people here. And so, I really appreciate it. Keep coming to class. Keep putting up with me. Send the quizzes to me. I'm going to be spending a lot of time grading over the next few days over the weekend, and I will be posting brand new grade stuff ASAP. All right, so maybe you remember this beautiful image at the beginning of this PowerPoint. This is where we were the other day, and we were working our way through it, and we worked our way through a lot of it. Right, I want to jump over this and go right here. We've looked at this already, but I want to just be sure that any of the details for class are covered. Quiz number 12 on biogeochemical cycles is due before class on Wednesday, April 15th. That's today. Email it. Look, if you didn't get it to me on time, you know what you should do? Send it to me as soon as you can. Okay? I mean, I'm way behind on grading, and so I can't afford to be real picky when I haven't been able to grade things and get them back to people. So quiz number 12, the one that was on, describe your favorite biogeochemical cycle, etc. That one was technically due today. I mean, I'm always going to give a due date. And then quiz number 13, the one that has to do with population interactions, and I'll remind you what those are, is due Monday before class. And so just go ahead and email it to me. Some of this other stuff down here, like the ecological footprint, due April 27th. Hey, did anybody try and look at the ecological footprint just to see that the link is right and all that kind of stuff? I updated the link at the beginning of the semester, but I'm not surprised. Nobody has looked at this now. Everybody's got plenty of stuff to do, but this is technically due the 27th, which is what, 1.5 weeks from now. So if somebody does go and try and go to the ecological footprint assignment, which is on my PIMA in the handouts and posts, if you have any trouble with the link, please email me and let me know. Okay. Tonight's topic, like it says here, is ecological community and ecosystem structure and function, and ecosystem energy and ecosystem services. A whole bunch of different interesting things to talk about. And then, of course, we'll set aside some time at the end to talk about the Home Ecosystem Lab. Some people have been sending me Home Ecosystem Lab data, which is wonderful. I'm happy to look at it. But, technically, we're going to make this Home Ecosystem. All of this data is going to be due in the first week of May. And I'm going to attach a huge amount of points to it. So if you want an A in this class, then devote the time and energy it takes to gather the data. I've still got one other thing that I need to attach that I have not put up there yet. It's the portion of this lab that deals with biodiversity. And it is also a survey you will do in your house. And I will get that updated and posted as quickly as I can. Any questions on the stuff that's right here?
Mr. Mackey, this is Sydney. I'm sorry to interrupt. When you say here, I don't see what you're showing. I only see your face.
Oh, okay. There is a document up here. So let's see what's going on. You're right. I'm not presenting anymore. What stops me from presenting, I wonder? Here I come. I'm already recording, so the stuff was recorded, but all right, so I'm going to go back to that document. I appreciate it, Sydney, that you told me. This document, by the way, in case we didn't see it, is the third slide in third slide here. Okay. Now, as far as ecological footprint goes, let me just tell you, it is document number. Oh, it's document number 11. Document number 11 in the handouts and posts on our drive. Has anybody else seen it? I mean, is it somehow missing from there? I have it listed here, so I went and double checked to see that it's document number 11. So honestly, you got to keep track of all these documents. There's about 25 documents up there now, more than I usually post. And so document number 11 is the ecological footprint. And it's pretty self-explanatory. If you read it, you should know what to do. There's a computer link to go to a site where it asks you a bunch of personal questions. You know, how often do you fly in an airplane? How many cars do you have? How many houses do you have? You know, how many pets, etc. And then it gives you a number. It tells you how many Earths it would take to support everybody if everybody lived like you. And like I said the other day, the minute you put down that you are in the United States of America, it automatically kind of starts at about 3 planets. So what that means is that if everybody wanted to live like us, everybody wanted to live like us, we would only need a minimum of 3 planets to make us do that. All right, Lisa, I'm going to go and check this. I mean, here it is. I've got this still live here. Here's handouts and posts for this class. Let me go down all the way down to document number. Oh, you know what? Maybe you didn't see it because in general, when you go to this page, it defaults to 20 documents. So you have to go down and toggle to 30 because there's 25 documents now. And now I'm going to scan all the way down. Here's document 7, 8, 9, 10, 11. There it is. Lisa, can you see that? Can anybody see that? Uh-oh. Nobody can see it.
No, yeah, we can see it.
Oh, okay, good. So everybody saw that. Here was probably the problem for Lisa and other people who couldn't find it. It only displays 20 documents by default. So if you wanted to display more than 20 documents, you have to go to the top. There's like a little toggle switch up around here, and you just toggle it to 30 or 50 or 500 documents or whatever. But it's on the second page is where it is, because we've got 25 documents now. All right, and I'm going to keep adding to it. All right, good. Thanks. I'm glad you can find it. I want to make sure people can see what they need to see. I mean, it's complicated enough without issues and problems like that. All right, so I'm going to go back to that PowerPoint. And I know I am presenting now because it says I'm presenting. So I think it's safe to assume that people can see this. And I don't know what happens when I do this. It's much harder to read then, huh? Okay, where am I? Okay, there we go. Sorry. You know, you got to do something to distract yourself, I guess. All right, so class business, there we go. That's the plan for tonight. All right, so now I'm going to zoom through all of this. I thought this was, you know, interesting stuff. What we were talking about at the end sort of was about these population interactions. Remember that back here, we were talking about population interrelationships. I keep calling these population interactions, how one species interact with another. Okay, so let me just make sure that that's crystal clear. Interrelationships. relationships between populations equals population interactions. Right, just so you know that when I use that terminology, that's what I mean. You know, this just jumped into my mind, but and it seems kind of crazy, but is anybody out there watching that Tiger King show, or whatever it is? Kind of a show that I hear about. I have not watched it yet. Has anybody watched it?
Yeah, it's so good.
Is it good? So
Yeah.
let me ask you a question. Does the guy have a liger? Liger?
Yeah.
He does. Is it huge?
Yeah, I think it was him who had it. Someone had one though. Yeah, I didn't know it was a real thing, honestly. I thought that was fake.
No. Well, you know, I feel as if I might have talked about it in class. A liger is what you get when you breed a male lion with lion plus female tiger. And this equals the biggest wildcat. Biggest wildcat. That's why people want it, because it's big. Now, you know what? If you bred a male tiger with a female lion, guess what it would be called? It would be called a Tiyon, right? Because the first letter, it refers to the male, and the rest of the word refers to the female. So lion plus tiger equals liger. Tiger plus lion equals Tiyon. And I mean, I know why people want ligers. They're big and they're impressive, and people will pay big bucks. You know, male lions and female tigers do not mate in the wild. This is not something that happens in nature, really. Since tigers and lions they may be closely related, but they're technically not the same species. When they produce ligers, those ligers are going to be sterile, and they are not going to be able to reproduce themselves. They're not going to be able to mate and form baby ligers from parent ligers. Just because two different species, when they mate, it causes some weird physiological issues. But I thought I had heard that they had a liger, and honestly, that might encourage me to go watch that show so that I can see what the liger looks like. All right, sorry, I got off track. You know me, I'm thinking about giant cats, just like I think about cats all the time. So interrelationships, remember these are population interactions: competition, predation, commensalism, parasitism, mutualism. And we talked about these the other day, and we talked about various different possibilities. In the end, though, here's a quick summary. In a mutualistic population interaction, both species benefit. In a predation population interaction, the predator gains and the prey loses. In a parasitic population interaction, the parasite gains and the host loses. In a commensal interaction, the commensal gains and the host is unaffected. And in a competition population interaction, it's really a negative thing for both species. When you have to compete for basic resources, it's never good. I mean, I could think of examples of this outside the door in the desert pretty easily, right? So, for example, a mutualistic reaction right out here in the desert might be the reaction that happens between lesser long-nosed bats and the saguaro cactus that they pollinate. Or when you see a bumblebee pollinating a flower, that's a good example of mutualism. Predation, well, I mean, that would be a bobcat eating a kangaroo rat. Parasitism, well, out here in the desert, there are examples of parasitism. One of the most famous examples is mistletoe, a bright green plant that grows on palo verdes and mesquites and acacias. It basically sucks into their nutrients and uses them and can potentially cause big problems for the plant. Again, though, you know, when I think of parasitism, I also think of something like just good old fleas or mites that might live on a pack rat or on a bobcat or something like that. Commensal, well, there was a pretty good example of commensalism the last time. It showed how a snake can live in a burrow that was made by a rodent. The snake needs that burrow and benefits from that burrow, but the rodent is long gone and unaffected. Also, the elf owl that lived in an abandoned saguaro nest that was made by a woodpecker. And then as far as competition goes, well, you know, so you saw the picture I showed the other day of a bobcat and a coyote competing for other small rodents to eat. So keep intact this stuff right here, just in case you want to make a note. This is the stuff I'm referring to in quiz number 13. Quiz number 13. Take a look at this page. Quiz number 13. So let's, this is slide, let me see if I can get the numbers. I think it's slide 10. I'm going to get that actual number. Okay. And I didn't get it. No, it was slide 19, I guess. Slide 19 of 61. I'm going to reduce it for a second. I'm going to go over here to the chat line, and I'm going to put Wiz 13. Ooh, I better spell it right. Wiz 13 answers on slide 19 in PowerPoint 008. Okay. Just in case you're interested, might be helpful. Okay, up here. So we were talking about population interactions. We took a look at some very specific examples. In the quiz, I am asking you for specific examples. So, but feel free to Google these and find out some specific examples. I'm just slowly working my way through here. And here's where we left off the other day, right? So I'm on slide 29 of 61. Oh, maybe we were a little bit beyond this, but I think this is a good place to go. Remember, when it comes to ecosystems, there are these two fundamental processes, right, that hold the ecosystem together, that structure the ecosystem, that basically structure the way the ecosystem looks, how complicated it is, how many species there are, all kinds of amazing things. And both matter and matter cycling, that's biogeochemical cycles plus, and a one-way flow of energy is a part of this really important process. So we've talked a lot about biogeochemical cycles and the movement of matter. Does anybody have any questions about matter cycling and that kind of stuff? I mean, biogeochemical cycles. If anybody has any questions, I would be so happy to try and answer them. Okay. Well, then the next thing we want to talk about, because it's equally important in creating the structure and function of ecosystems, is the one-way flow of energy. So I think I'm reviewing here, but let's just talk quickly about energy. Energy is the ability to do work. It's not a very satisfying definition for me, but believe me, this is a definition that is straight out of the dictionary, straight out of the physics textbook, chemistry textbook, even the biology textbook. It's the ability to do work. Well, what does work mean? Honestly, work can be lots of different things. It can be movement. It can be building molecules and creating chemical bonds. It can be breaking apart molecules and loosening chemical bonds. It can be the ability to produce sound or light or heat. All of these things fall under this general category of what we might call work. I mean, when you walk up a flight of stairs, you are using more energy and you are technically working. Okay, so movement can be a really big one. Now, energy quality, the next one here, is really, whether the energy is useful or not. There are some kinds of energy. Perfect example, electrical energy, the stuff that comes out of the, comes out of the electrical socket on your wall. Very, very useful kind of energy. I mean, think of all the things you can do with electrical energy. But one of the least quality energies is low-level heat. Now, the heat that radiates off my skin, that is low-level heat. There's virtually nothing I can do with it. It is energy, but it's low-quality energy. Lastly, energy efficiency, how much work we get per unit of energy used. This is kind of where we left off the other day, where I was saying, look, you know what? Some devices we use are very energy inefficient. I mean, a race car that is just super tuned, the highest, best race car you could, possibly create, would be probably about 25% efficient in its energy use. And what that means is that when you put gas in it and you burn gas in it, about 75% of the energy released by that gas is not going to do anything for the car. Only about 25% of the energy is going to be useful. I mentioned this one the other day because this one's always seemed very interesting to me, is the incandescent light bulb. That's the Thomas Edison style bulb. I have to say I don't have any of these in my house anymore. The Thomas Edison style bulb is really inefficient when it comes to making light. It is 5% efficient. When you put 100 units of a good quality electrical energy into a light bulb like that, the old style Thomas Edison incandescent bulb, only 5 units of energy emerge as light. It's 5% efficient. 5 light units out of 100 energy units. It's 95% inefficient. And how do we experience that inefficiency? It's the heat the bulb makes. Now, I don't know, I mean, I kind of hate to admit this, but when I was a kid, I had one of those Easy Bake ovens. They still have Easy Bake ovens. And I had one of those Easy Bake ovens to play with. I was a young gourmet. And what was amazing is in that Easy Bake oven, they used a light bulb as the heater to cook your, Easy Bake oven cake or whatever. The light bulb was a heater. Now, if you use it that way and you don't care about light, well, then it is 95% efficient because it makes lots of heat. Every 100 units of electricity you put into it, it makes 95 units of heat. And if you're using it as a heater in your Easy Bake oven, when I was a kid again, we used to hatch chicken eggs and we would use lights as a heater. So they were pretty darn efficient. If you're thinking about the light bulb from a light perspective, it's really inefficient. If you're looking at it from a heat perspective, it's really efficient at making heat. Anyway, we're going to talk about energy quality and that kind of stuff more. So let's talk about the laws of thermodynamics. Now, this is where I was the other day when we started to get cut off. I apologize, but I want to say this again, because this is exactly what I was saying, I think, last time we were cut off. What does thermodynamics mean? Well, thermo means energy, and dynamics means movement, really. It means movement, activity. So these are laws that deal with energy movement. And they're pretty famous laws. And they deal with the movement of energy. The first one is called the first law of thermodynamics. And it basically says this: energy cannot be created or destroyed, only transformed. Well, I'm going to add a tiny bit of information to that and say first law thermodynamics means a couple things, right? It means the energy in is always equal to the energy out. Okay? The energy that goes into a system, it isn't created or destroyed. It goes in, it's transferred and transformed. Energy in equals energy out, right? Energy is not created or destroyed. That's what the law of thermodynamics says. It is just transferred from one place to another. And I'm going to go back and just transferred from one place to another, and it is just transformed from one type to another. Because energy is not transferred or transformed, if you try and account for it, energy you put in is ultimately going to be equal to what energy comes out. So I don't know. I want to almost think of an example of this in my car. And when I think of my car, I think, okay, I'm going to put a pretty high quality energy in my car. That is a fossil fuel distillate called gasoline. It is really rich in energy. If I put, let's say, 100 units of fossil fuel energy into my car, and I use up that 100 units of energy, if I could keep track of that energy, here's what I would discover: that some of that energy was transformed into movement energy. And that's why my car sped down the highway. Some of that energy was converted into sound energy, the sound that makes my car go, or it could be the rattling and all that, or it could even be my radio. Some of that energy is transformed into sound energy. Some of the energy, especially if I'm driving at night, is transformed into light energy that I spray out in front of the car so I don't run over someone's kitty cat. Another big use of energy is heat. I mean, my car converts so much fossil fuel energy, chemical bond energy, and fossil fuels into heat that I have to have a whole system on my car just to take that heat away. Otherwise, it will melt the engine down. So the first law says energy cannot be created or destroyed, only transformed. And like I wrote over here, energy isn't created or destroyed, it's just transferred from one place to another and transformed from one type to another. You can take chemical bond energy in gasoline, convert it into light energy, electrical energy, heat energy, sound energy, movement energy, all those different kinds of energy. Now, the second law of thermodynamics says this: energy degrades to a less usable, lower quality form. And I'm going to restate this again, too, and say, look, the second law of thermodynamics says that whenever you use high quality energy, whoops, what happened here? Thermodynamics. Thermodynamics, there we go. Second law of thermodynamics says can't even type. It's been a long day. That whenever you use high quality energy, some, maybe most of the high quality energy. Man, what is it doing here? It's crazy. The cursor is just moving. Wow, I don't get it. Is always converted to low quality energy. Now, believe it or not, I'm of course going to relate this to biological systems because we're studying biological systems. But here we go. I'm going to post it. I hope I got it right. It says this, second law of thermodynamics, please copy this down, says that whenever you use high quality energy, some, maybe most of the high quality energy will always converted, sorry, I misspelled converted, to low quality energy. So what does that mean? Just as an example, it means that when you put high quality gasoline in your car, most of the energy in that gasoline is going to end up as heat. Heat, that's pretty useless. I mean, there's hardly anything you can do with it. Oh, I've heard of people, you know, putting some food on their engine and cooking it while they drive. I've heard of that happen. I am not saying that there wouldn't be some really weird creative way to use some of that heat, but let's face it, most of that heat that is produced as a result of us burning gasoline in our car, most of that heat is just going to radiate out of the car and it's going to go into the atmosphere and it's going to radiate into space. So it's true. We put a really high quality energy, that is fossil fuel gasoline, into our car. And a very large percentage of it is ultimately converted into heat energy that can't be used for anything. It's useless energy. I mean, let's face it, can you run a car on heat energy? Well, most of our cars are not designed to do that, right? I mean, it's not impossible, right? You could, I mean, I remember seeing movies and pictures of a train where they boiled water using heat from firewood, and they were able to use that boiling water to run the train. But that's really reaching. And again, even in that case, a lot of high quality energy in the wood would end up being converted into low quality energy. So remember that part of the big deal here is that matter and energy flow through an ecosystem. And what happens there is energy comes in as solar energy and it gets converted into chemical bond energy. It gets transferred and transferred and transferred and transferred. The energy flows like this. Now, every one of these organisms here is going to turn a lot of that energy into heat energy, and that's just going to radiate off. They don't really show that. A lot of it's going to be converted into heat energy. I mean, my body produces as much heat energy as a 60-watt light bulb 24/7. And that energy has been transformed from the chemical bond energy that I ate. And then I use that chemical bond energy to move muscles, etc. and ultimately it's converted into heat and it just radiates off my body. I mean, I suppose on a cold night it might be helpful, but really there's not much I can really do with that energy. Energy enters as solar energy and it leaves mostly as heat. Okay? Now, this is interesting. If you are looking at a big food web like this and you start plucking species out, what can actually happen is that you can really mess with the ecosystem. I mean, it will change the interrelationships if you were to pull some of these species out. Oops, sorry. Let's say for a minute you took away the sawgrass. Well, then anything that ate sawgrass would suddenly have nothing to eat. And so things that ate sawgrass, they would die. And then those creatures were food for a food source, meaning an energy source and a molecule or atom source for other creatures. So those die off. And then when those die off, other creatures die off. And ultimately, just by removing this one species here, the sawgrass, which happens to be a producer, which is one of those amazing creatures that can take solar energy and water and carbon dioxide and convert it into sugar, which is packed full of energy. When we talk about these, let's talk about trophic levels, but you know what? It's 7 o'clock. Can we take a quick 10-minute break? All right, I kind of need to run to the restroom myself. So we're on an official 10-minute break right now. Believe me, I'm going to be back in 9 minutes and ready to go back to work, okay? 10-minute break. All right, here we go. So we're back here thinking about trophic levels, and we've talked about this before. But let's go just real quickly, take a look, because what we're looking right at here is we're looking at the structure of an ecosystem, an ecological community, kind of where ecosystems and ecological communities overlap. At the bottom, we've got producers, plants that are able to do photosynthesis. Above those, we have primary consumers. Sometimes these are called herbivores. Above them, we have secondary consumers that eat them, that are called secondary consumers. Also, they could be called carnivores since they eat only meat. These things here, whoops, I lost it. These creatures here eat only meat. Tertiary consumers, again, these are another level of carnivores, and quaternary consumers, another level of carnivores. I mean, this alligator eats this gar eats a smaller fish, this smaller fish eats this shrimp, and this shrimp eats the producers down here. But notice something that's interesting. When you go from one trophic level to another, when you go from the producer level to the herbivore level, guess what? 90% of the energy is lost as heat, and 10% is actually transferred. 90% lost, 10%. 90% lost, 10%. 90% lost as heat, 10%. Now, one thing that this trophic level diagram doesn't really include is this level that's over here, the decomposers and detritivores. And they feed on the dead bodies, they feed on the waste products, they feed on the dead leaves, etc. They are super important in recycling matter back. So, you know, for what it's worth, producers like this, they provide energy for all of this, but then there's leftover, I mean, there's parts of bodies, etc. They get decomposed, and then once decomposed, they go back into the soil to help nurture the producers. So what we're really looking at here, if you start here, is you see matter recycling. But then when you look at energy, the energy comes in from the sun, and most of it ultimately leaves as heat. In fact, you know, I guess in the long run, virtually all of it's going to be converted into heat. We can boom through these. Producers convert light energy. Here's something that's worth mentioning, what's called the rule of 10. The rule of 10 has to do with these 10s here. When you transfer energy from the first level to the second, to the third, to the fourth, to the fifth, only about 10% transfers. 90% is lost as heat, or it's used to, support the metabolism of these organisms. This is called the rule of 10, or the 10% rule, and it basically says that as energy is transferred from one level to another, oh my gosh, 90% of it is either used or produced as heat, and only 10% of it becomes new biomass in the next level up. That's kind of amazing when you think about it, this 10% transfer. However good quality the energy is, solar energy is pretty good quality. As it is transferred from level to level to level, most of the energy ends up being converted into heat, and a very small percentage of it ends up being converted into the next level up. So in this one-way flow of energy, you have what's called a pyramid of energy, and that pyramid of energy looks a little bit like a pyramid that I'll show in the next slide. There's also a pyramid of numbers, meaning that there's lots of plants that are necessary to provide energy for fewer herbivores, for fewer carnivores, etc. And at least a certain sense of that is because, as you transfer from one level to another, an awful lot of energy is converted into heat. So what does this have to do with our diet? Well, take a look at this pyramid here and think about this this little food chain. 1,000 tons of grass is enough food to produce 27 million grasshoppers. Now, those 27 million grasshoppers, that's enough food to feed 90,000 frogs. And those 90,000 frogs are enough to feed 300 trout. And if we're sort of talking about a big picture like a year, certainly one human could eat 300 trout in a year. So really that 1,000 tons of grass that's down here, all the energy in that 1,000 tons of grass, because it's transferred up and we've got the 10% rule, means that we can ultimately support one human. So I mean, these numbers are estimates, but they're not bad estimates really. So 1,000 tons of grass produces enough energy for one human to survive for 1 year. So it kind of makes you think, right? Because after all, couldn't a human eat grasshoppers? Couldn't a human eat frogs? Couldn't a human eat trout? Couldn't a human eat grass? Well, it's worth considering. If, for example, humans decided that this one human that ate 300 trout based on 90,000 frogs and 27 million grasshoppers, 1,000 tons, what if instead of eating trout, the humans decided to eat frogs? Well, then 90,000 frogs would feed 30 humans, not just one, but 30. Now, I'm not a big fan of frog meat. I've eaten it before. My mother loves frog legs. But take a look. Because of the 10% rule, all of this energy can only support one human. Because we want to be up there as the top carnivore. But if humans were willing to, say, change their dietary habits a little bit, we could support much more humans and feed them frogs. Now, what about another condition? What if instead of 1,000 tons of grass producing, producing enough energy for one human, what if humans decided they were going to eat grasshoppers? Now, again, there are parts of the world where people eat grasshoppers all the time. And I've been told that you can grind grasshoppers up and turn them into something that's kind of like meat. You could eat them, etc. So if, for example, humans decided to eat lower on the food chain, and instead of eating trout or frogs, they decided to eat grasshoppers, then look how many humans you could support. Why? Because as energy is transferred, remember, as it's transferred from here to here to here to here, a lot of it is lost. It's just turned into useless heat energy. The lower you eat, the less energy loss there is. So it's worth considering. I'm not really quite sure that I'm ready to eat grasshoppers yet, but anyway, what if instead these humans decided they were going to just eat grass? They were going to be a vegetarian diet. They were going to just eat producers. Well, then look how many humans could be supported. Come on, cursor. 2,000 humans could subsist on 1,000 tons of grass. Like it says here, a meat-based diet requires up to 10 times the land area to feed a person relative to a plant-based diet. And this is one of the reasons my daughter told me back when she was 10 years old she was going to be a vegetarian, because she read a book that said, look, we need to eat lower on the food chain. People who eat high on the food chain and eat all different kinds of meat and stuff, they are going to be participating in a system where a ton of energy is lost. The lower down you eat, the less energy loss there is. Let's study this. Now, I'm only kidding. This is a big food web that actually connects multiple communities: the aspen community, the willow community, the immature aspen community, the prairie community. These are our 3 ecological communities that are all linked together by the transfer of energy and matter. So pretty amazing. Now, again, I'm not going to go through this in any details, but the bottom line is that here's where we really are seeing evidence of an ecosystem where matter and energy are flowing through these different ecological communities. So a food chain, we've talked about this a little bit, is a series of organisms each eating or decomposing the preceding one. So I'm not going to ask you to do this, but it might be worth thinking. I might decide to put this on a quiz in the future. We've talked about food chains in the Sonoran Desert for sure. So, I mean, one that comes to mind for me would be, okay, there are many plants like, let's say, wild mustard that produce seeds. Those seeds fall on the ground and rodents and ants eat the seeds. And then along comes one of those horned lizards, which eats ants, and it eats the ants. But then the horned lizard gets eaten by a big snake, and the big snake gets killed and eaten by a coyote. So we've got levels and levels of food chain, though we're watching energy and matter go from the soil to a plant that produces seeds, to an ant that harvests the seeds, to a horned lizard that eats the ants, to a snake that eats the horned lizard, and a coyote that eats the snakes. We easily think of food webs and food chains. So this one-way flow of energy means that systems like this have what's called the net primary productivity. This is really the rate at which plants produce chemical energy through photosynthesis. Remember what photosynthesis was? I wrote it on the board before. Photosynthesis is where plants use solar energy to cram carbon dioxide and water together to make sugars and oxygen, both things we need. That's why we have to hug a plant every day. Now, you have this big total, well, you have a total amount of energy that is, a total amount of energy that's produced minus the rate at which plants use the chemical energy, right? And what's left after you take away the gross primary productivity and you subtract the, the cost to do business for a plant, you get the net primary productivity. This primary productivity is like profit in an ecosystem that can be used to supply the energy needs of animals. So which biomes on Earth do you think are the most productive, the least productive? I mean, here's a few biomes: agricultural land, temperate grassland, open ocean, desert scrub, tropical rainforest, tundra. I mean, there's all these different ones. Which are the least productive and the most productive? And I mean, in this sense, I mean, which of these biomes, groups of ecosystems, which of these biomes produces the most profit that's available to other organisms to help them live their lives? Well, take a look at this. This is kind of interesting. This is the average world net primary productivity. Okay? Notice that, oops, you know what? Let me go down a minute. I want to go down. Okay, so here are some primary productivities for sort of different biomes. Notice that because there's a lot of open ocean, the amount of productivity that's contributed to the biosphere is pretty high. Tropical rainforests, lots of energy produced. Temperate rainforests, lots of energy. Here's agricultural land, right? So these are natural systems. Here's agricultural land, then temperate grassland, estuary, swamps and marshes, desert scrub, we're near the bottom, tundra. That's the subarctic stuff, is really very, very unproductive. Now, net primary productivity. This last one was primary productivity. And this one is primary productivity too. And honestly, I don't know what I did here. I just made the slide twice. I apologize. Okay, where am I? I'm not in the right spot, I guess. And down here, really, this is what's interesting. I'm sorry I missed this. I apologize. This is total primary productivity of the planet. The open ocean contributes a lot to it. This is the total sort of profit made by the ocean ecosystem over the entire planet. All right, but now take a look, because now this is the same thing, the profit or productivity, but now it's per meter squared. And that's a big difference. Before, it sort of summed up the productivity all over the entire planet. But take a look now. When you consider it by just a square meter, how much productivity there is, notice rainforest way high still. There's a lot of tropical rainforest, and it's really, really productive. What about open ocean? Well, before, open ocean was really productive when we sort of looked at the entire productivity for the entire planet. But when you look at one little square meter and how much productivity it is, the open ocean is very low. Desert scrub, very low. Tundra, very low. Agricultural land, temperate grassland, in the middle. Swamps and marshes and estuaries, though, they are way up there. These wetlands that are relatively rare, they really don't contribute a lot to the entire world's productivity. But on a meter by meter basis, you know, in a small area within them, they are super, super productive. And so it is kind of interesting that the fact that these are so productive really produce a lot of profit. But yet, on a global basis, they don't add much to the entire planet. It means that these things must be kind of rare. Swamps and marshes and estuaries that they sometimes call wetlands are pretty rare, and they're maybe really, really productive, but they're pretty rare. This is one of the areas that they're always talking about preserving, these swamps and marshes. Because these swamps and marshes are so darn productive, they can be a great place for fish to lay their eggs and other organisms to lay their eggs, because there's going to be a ton of energy profit in those spaces. So if you damage swamps and marshes and estuaries, you damage these wetlands, you can really have a huge effect on populations of fish that can be important, game fish and things like that. So again, we've been talking sort of all along about the Everglades, because we've got this food web for the Everglades, but they can be very productive as long as, you know, we've got all the right players, everybody's in here and they're doing their job. If you change the community structure, it can completely change the community composition. This species right here, the American alligator, it is really famous because it is what is called a keystone species. And what a keystone species is a species that has a great impact on an ecosystem. It has a greater impact than you would think. Often predators can have really profound impacts on the way ecosystems function. And so there are keystone predators that are keystone species that if you take those predators away, it causes the entire ecosystem to collapse. And that's certainly true in the American alligator. What the American alligator does that is so important is it actually digs a hole. It digs a hole in the Everglades. And when water levels fall, there's a little pond created. The gator lives in that pond, sure. But other creatures that would die if there was no sort of little hidden gator hole, those manage to live during dry times or weird times in the Everglades. if this alligator wasn't around and it didn't dig this hole, then this little pond wouldn't exist, and all the creatures that are kept alive in it would also fail to exist. So they've been trying to restore the ecosystem down there in the Everglades for sure. In 1992, the Water Resources Development Act enlisted the Army Corps of Engineers to investigate damage to the Everglades. The canals and levees had dramatically altered the water levels. Ecosystems were being starved. They were being affected by too much salt water, excessive nutrients, and non-native species. In 2000, the Comprehensive Everglades Restoration Plan became a 30-year plan for Everglades restoration through 60 construction problems, 60 different projects, all designed to restore the Everglades to its natural condition. Because remember, the historic flow had a lot of movement down from this lake down into the Everglades and ultimately into the ocean. A lot of that got diverted mainly because people were building houses and they were putting Walmarts and grocery stores and everything else in there, and they changed the way the water flows. And that meant that the Everglades ecosystem here was damaged, destroyed, fragmented, etc. The ultimate goal is to unfragment it as best as possible and restore the normal flow in order to preserve the Everglades at a better level than it was. So, you know what? I think I'm going to stop here for today. This is a really important topic, and I don't want to blow through it too fast, and that's where I'm kind of headed right now. I'm going to start on this slide next time, ecosystem services. But if you wanted to take a look at the next PowerPoint that I'm going to be working on next time, the one that deals with population ecology, very interesting. Then you can take a look at it. It is document number 0010. Nope, yeah, I said that wrong. 0011. So in our folder, the handouts and posts, document 0011 is the new PowerPoint on ecological populations. And like I said before, Sydney, if you would ask me, or Sarah, if you would send me an email, I would send you a copy of it. All right, so this is where we're going to come back to next time. Okay, I know I boomed through a lot of material here, but you've got this PowerPoint, so you can go back and study it and think about it. And if you have questions about it, you can email me them. You can ask me about it, etc. The quiz that I posted that's due next Monday is on population interactions, which is all stuff that's right at the beginning of this PowerPoint. But then the next PowerPoint I'm going to produce has to do with energy flow. So ecosystem energy and ecosystem services and those kinds of things. Those are going to be the next quizzes that I produce, okay? So the next one is going to be document 0012, and it is going to be on ecosystem energy. And then 0013, I think, is probably going to be on ecosystem services. Right, and then, well, I better be careful because I'm going to be posting some other things. But here's what we're going to come back to next time, page 5961, because this is just too interesting of a topic to try and blow through just because I'm tired, you're tired, etc. Okay, I'm going to shrink this down. So in the last few minutes of class, I guess I want to ask how people are doing with the lab work. I mean, are people able at their homes to gather this data? I mean, I'll remind you again that this is a big lab. I will ultimately be asking you to send me this data. I will be asking you to look at the data and analyze it so that you can point out some patterns and trends to me. And I'm also going to ask you about conservation because I want people to look at their data and start to think eventually about how they could reduce the amount of garbage they produce. How could they reduce the amount of energy they produce? How could they reduce the amount of water that they use? Okay, and so we're headed in that direction. And then again, one of the things I need to provide for you is the biodiversity survey, which is just going to ask you to look in your refrigerator, look in your medicine cabinet, look under your couch, and look under your bed, and all that kind of stuff, and see if you can find some Easter eggs. No, not Easter eggs. If you're going to be able to find some examples of unusual and interesting organisms that contribute to your household. And here's what I mean. A jar of salsa probably has at least 5 different organisms that are part of it. Of course, it has tomatoes. It has at least one kind of chili. It probably has cilantro. It probably has onions in it. It certainly has garlic in it. So I said 5 different organisms that are part of your jar of salsa. And oh my gosh, if you have one of those kinds of salsa that has black beans and corn in it and all that, you've got other organisms. So one of the things I'm going to ask you to do in the biodiversity part of this is look in your refrigerator and try and identify organisms that are part of the foods that you eat. Now look, I'm not asking you to find some living thing in your refrigerator, though there are living things in your refrigerator. A head of lettuce is alive. And when you eat it, you are eating something that's alive. Celery, probably alive. Apple, probably alive. Cheeseburger, no, not so much. Probably not alive. But a cheeseburger has cheese that was made using cow's milk. It has a meat that was derived from cow's milk, from cow muscle. It has barbecue sauce on it that includes ketchup and vinegar and things that were made by organisms. So I'll get you that biodiversity survey by next time. But as it is right now, I'm hoping people are working on the water portion of it and the electrical portion of it and even the garbage portion of it, okay? So that you're gathering data so you can eventually tell me about your household, your use in your household of these planetary resources. Okay. So why does it feel like you're in Mexico again, Syria? Were you required to keep track of water,
Yeah, we were
electricity,
required.
and things? When,
Yeah, so we were every time or in summertime we would go to Mexico in this little town called El Claro where my nana grew up. So we would
Mhm.
put the water into the gallons and measure what we use so all the family can use, like portion it out.
Oh,
Same goes for electricity.
right. So you were basically rationing water, really.
Yeah, more like yeah.
You probably learned some ways to make water last longer, which I think is great. I mean, I'm hoping that, and let's face it, if we were in class at Pima, we would be doing this differently. We would be working in groups, and groups would be responsible for different things. But now it's, and sometimes in those groups, let's face it, you've been in a group in classes and maybe even in my class where there were people who were working hard and kind of driving the group, and then there were people who were just, I hate to use this term, they were parasitic, right? They were just sort of tapping into your energy and all that kind of stuff. So the bottom line is that now you're getting to do it all yourself, and if somebody is doing it well, they're going to get a lot of points on it, and it's going to it is going to add to your grade and make your A even stronger. If someone decides they're not going to do this, they're going to lose a significant number of points as a result. And but at least on them, it's not on you. If you're doing work, you will benefit because of the points. Okay. And so plug away at it. I mean, I don't think you should be spending more than maybe 8 hours a day on it at the most. Okay. Of course, I'm only kidding. I think, probably an hour a day, and you are doing lab work, which is nice, and you are producing data, which will be useful to us, and you are participating in a lab that will be worth a lot of points and help you lock in your A. Okay? So that's about the best thing that I can say about that.
I have a question.
Yes, go ahead. Is it you, Caitlin?
Yeah. After we get all the lab data, are we gonna have to write about our information?
Yes, I'm going to ask you to explain some of the patterns that you see in your home. That's all.
Oh,
It's not going to be an elaborate write-up. It's going to be about patterns that you see in your home, in terms of your water use, etc. So it's not going to be a big elaborate thing, but it will be. It will absolutely be. You will be analyzing the data at some level. Okay, and that's. I mean, I'm happy. I have to be honest with you that in my other class, I teach, this other class 3 times a week, and it's very difficult to do labs. And that's a class where I do microscopes and some other kinds of stuff. We're having trouble doing labs. I'm so happy in Bio 105. We are already set up to do a lab that you basically do at home. So that'll probably put me out of business, right? They probably won't need, old dinosaur classroom teachers like me anymore. They're just going to replace me. They're going to replace me with younger, certainly taller, more hirsute people, more attractive people who know how to do the online stuff great. So I don't know. This might be the last semester I ever teach. You never know. People may decide that they like the virtual teaching so much that they tend to do that a lot. I hope not. I like teaching Bio 105, and I like being in the classroom teaching Bio 105. But I'm really happy that we're all here together and we're all surviving. So my best advice that I can give you now is socially distance, wash your hands a bunch, use Purell if you have it, and let's all not get sick. Let's all do really well until they finally get a vaccine and we can get vaccinated against it and never worry about it again. Okay? So hang in there, people. I'll see you on Monday night at 5:45, or Monday, evening at 9:45. Okay?
All right, thank you.
All right. Have a good weekend. I'll be grading. Hang in there. Bye.